us have heard of dinosaurs, the colossal beasts that once ruled the earth, towering, ferocious, unforgettable. But here's the truth. Dinosaurs were not the first rulers of our planet. Long before a single dinosaur ever took a step, Earth had already lived through entire forgotten worlds. Oceans filled with bizarre monsters, forests stretching into endless horizons, swarming with dragonflies the size of birds, and predators so nightmarish they make dinosaurs look familiar. This is the story of those ancient kingdoms, built and destroyed by unimaginable cataclysms, a saga of survival, extinction, and rebirth. Tonight, we'll travel further back than you ever imagined, to witness the rise of life, the battles for dominance, and the strange empires that thrived long before the age of dinosaurs. 4.5 billion years ago, Earth was a world unrecognizable, a seething sphere of fire and stone, scarred by impacts from space. For millions of years, asteroids rained down, each collision reshaping the surface, boiling oceans before they had even formed. The sky was choked with volcanic gases. Lightning split the darkness. And yet, in the chaos, the seeds of something extraordinary were stirring. Against all odds, water gathered in the planet's basins. Vast oceans spread across a landscape still raw and young. In those alien seas, chemistry gave way to biology. Simple molecules collided, joined, and split apart again, until, somewhere in the depths, life emerged. It did not begin with great beasts or towering plants, but with the smallest of architects, microscopic cells. Invisible to the naked eye, they were fragile, but they carried the potential to transform the planet forever. These earliest organisms thrived in shallow, sunlit waters. They built layered colonies known as stromatolites, still found in remote corners of the world today. To look at them might seem unimpressive. Mounds of rock-like structures rising just a few feet above the waterline. Yet billions of years ago, they were alive, bustling with microbes that performed an act of alchemy no creature had attempted before: photosynthesis. With every breath of sunlight, these organisms released oxygen, slowly, imperceptibly, altering the chemistry of the air and the oceans. At first, oxygen was toxic to many forms of life, poisoning the very environment that birthed them. Countless species vanished in this invisible catastrophe. But out of destruction came opportunity. Oxygen also made possible more efficient ways to harvest energy, paving the way for complexity, for change, for the rise of new life. This event is known as the Great Oxidation, one of the most transformative moments in Earth's history. Imagine the entire sky turning from a suffocating haze into a pale blue atmosphere. Oceans shifting color as iron dissolved into rust, painting the seabeds red. It was not a sudden revolution, but a slow awakening, taking hundreds of millions of years. Yet it marked the first step toward the planet we know today. Here, at the dawn of life, we see the pattern that will repeat across deep time. Life pushing boundaries, changing its world, and paying the price in mass extinctions and rebirths. The story of Earth before the dinosaurs is not just about creatures that lived and died. It is about life's relentless ability to transform a hostile planet into a living one. For nearly 3 billion years, Earth remained a microbial planet. Oceans swarmed with single-celled life, and the land above remained barren, a silent wasteland of rock, sand, and volcanic plains. But beneath the waves, something remarkable was slowly unfolding. Life was preparing for its first great leap, the transition from the microscopic to to the multicellular. Around 600 million years ago, during a time known as the Ediacaran period, creatures unlike anything we know today began to appear. They had no bones, no shells, no teeth. Instead, they were soft-bodied, their forms rippling gently in the currents of shallow seas. Some resembled quilted mattresses spread across the seafloor. Others looked like fronds anchored to the sand. And still others bore shapes so alien they defy comparison. These were the first communities of complex organisms, the earliest attempt at building bodies larger than a single cell. Among them was Dickinsonia, an oval-shaped creature that sprawled across the sediment like a living rug, absorbing nutrients directly through its body. There was Carnea, a leaf-like organism rooted to the seafloor, reaching upward but without leaves, stems, or flowers. And there were enigmatic beings like Sprigina, whose segmented form hints at the blueprint of later animals. Worms, insects, and even vertebrates. The seas of the Ediacaran were quiet compared to what would follow. There were no predators here, no hunters with teeth or claws. Life was peaceful, almost experimental, with different body plans emerging and vanishing, as if nature itself were sketching ideas on the canvas of the ocean floor. But this tranquility was temporary. The arrival of multicellular organisms set the stage for competition, and competition would ignite the engine of evolution. To survive, these creatures needed oxygen, and by this time, Earth's atmosphere had reached levels that allowed larger, more active bodies to exist. What had begun billions of years earlier with microbial photosynthesis now bore fruit. Oxygen became the fuel of complexity. With it came movement, sensation, and eventually, the drive to hunt. The Ediacaran biota, as scientists call this strange menagerie, represents life's first bold experiment with form. Yet, like so many early chapters in Earth's history, it ended in disappearance. Most of these creatures left no descendants. Their shapes, so alien and unfamiliar, faded away as new players rose to take their place. Still, their significance cannot be overstated. They proved that life could build bodies, could organize cells and tissues, and could reach beyond the microscopic. They were the overture to one of the most explosive and creative chapters in natural history. A chapter that would transform the oceans into battlefields and forever change the story of life on Earth. The Ediacaran seas were unlike any oceans we know today. Imagine standing on a shore 600 million years ago. No sound of birds overhead, no rustle of plants on the land, only barren rock stretching towards silent horizons. And yet, just below the water's surface, alien gardens flourished. Colonies of frond-like beings swayed gently, covering the seafloor in vast fields. Flat, ribbed organisms lay like living carpets, absorbing nutrients directly from the sand. Others resembled discs, ovals, or spirals, their bodies leaving faint impressions that would survive in stone for hundreds of millions of years. This was a world of forms that seemed more like living sculptures than animals. Some drifted passively, anchored to the seabed, while others may have inched slowly across the sediment. There were no skeletons, no shells to protect them. Theirs was a fragile existence, dependent on stable oceans and the newly enriched atmosphere of oxygen that bathed the planet. But beneath the surface of this quiet scene, profound changes were building. Oxygen levels were climbing higher than ever before, and ecosystems were growing more complex. In this new environment, movement became an advantage. Organisms that could crawl, burrow, or respond to light had greater chances of survival. Step by step, life was preparing to take on sharper edges, harder bodies, and more aggressive strategies. The Ediacaran creatures, for all their beauty, were evolutionary experiments. Most would vanish without leaving descendants, their body plans erased in the next great shift. Yet in their disappearance, they cleared the stage for what was to come. The tranquility of these seas was about to end in a burst of creativity and conflict. To scientists, the Ediacaran period is a riddle. Fossils from this time are rare, preserved only under the most delicate conditions. Their shapes are so alien that debates continue. Were they true animals, giant colonies of microbes, or something in between? Perhaps they belonged to entire branches of life that no longer exist, wiped away before the great drama of animal evolution truly began. What we do know is this: the Ediacaran world was the threshold. It was the final rehearsal before the curtain rose on the Cambrian period, an age that would see the invention of shells, claws, eyes, and teeth. The oceans were about to transform from peaceful gardens into arenas of survival, where for the first time in history, life would take on the roles of hunter and hunted. The story of Earth before the dinosaurs is not just about ancient giants. It is about the countless forgotten worlds that came before them. And in the fading echoes of the Ediacaran, we can sense the pulse of what's next. The explosion of life that would shape every future chapter. Around 541 million years ago, the planet entered one of the most extraordinary chapters in its history, the Cambrian period. In a geological instant, just a few tens of millions of years, the oceans transformed from calm experimental gardens into bustling theaters of innovation. This event is known as the Cambrian explosion, and it represents one of evolution's most dramatic leaps forward. Here, in the shallow seas, life began to reinvent itself with breathtaking creativity. Organisms evolved skeletons and exoskeletons, hard armor that offered protection from attack. Eyes capable of detecting motion and light burst into existence, granting predators a crucial advantage. Muscles and articulated limbs gave creatures mobility, allowing them to swim, burrow, and crawl in ways no Ediacaran organism ever could. The Cambrian oceans were suddenly alive with diversity. Trilobites, distant relatives of modern crabs and insects, scuttled across the seabed in vast numbers, their segmented bodies and compound eyes making them some of the most successful animals of the age. Brachiopods, shelled creatures that looked like clams, anchored themselves to the seafloor, filtering food from the currents. Worms of every shape and size tunneled through the sediment, stirring nutrients and reshaping ecosystems. But alongside these new defenses came predators. Among the most formidable was Anomalocaris, a giant of its time, growing up to 3 feet long. With large compound eyes, sharp-spined appendages for grasping, and a circular toothed mouth, it was the terror of the Cambrian seas. To its prey, soft-bodied animals and early trilobites, it must have been an unstoppable nightmare. This was the first arms race in the history of life. Prey evolved armor, spines, and shells. Predators responded with sharper claws, faster movement, and keener senses. For the first time, ecosystems were shaped by direct conflict. Survival was no longer simply about absorbing nutrients or drifting with the current. It was about escaping the hunter or becoming one. The Cambrian explosion also introduced body plans that remain with us today. Nearly every major group of animals, arthropods, mollusks, chordates, can trace their roots back to this period. It was as if evolution had suddenly opened a vast toolbox and begun constructing forms that would dominate Earth for the next 500 million years. In the span of a geological blink, the planet had gone from a world of strange, static organisms to one teeming with movement, vision, and predation. It was the dawn of complex ecosystems, the birth of food chains that echo even now. The Cambrian seas were not just alive, they were alive with strategy, conflict, and invention. The Cambrian seas were not just diverse, they were bizarre. Nature seemed to be experimenting wildly, testing shapes and strategies that ranged from the ingenious to the downright surreal. Many of these designs would vanish without leaving descendants, but others would lay the foundations for the animal kingdom as we know it today. One of the strangest was hallucigenia. At first glance, it looked like a creature from a fever dream. A tiny worm-like body, spindly legs on one side, and long spines jutting upward like defensive spears. For decades, scientists debated which way was up. They even reconstructed it upside down at one point, mistaking its legs for tentacles. Yet despite its odd appearance, hallucigenia was real, crawling slowly across the Cambrian seafloor in search of food, protected by its forest of spikes. Even stranger was Opabinia. Imagine a shrimp-like body with 5 eyes perched on its head, and from the front, a long, flexible proboscis ending in a claw-like appendage. With this bizarre tool, Opabinia could probe into the sediment or snatch small prey, drawing it toward its mouth. To modern eyes, it looks more like something from science fiction than natural history. Yet in the Cambrian oceans, it was just one of many experimental designs. Then there was Wiwaxia, a soft-bodied grazer covered with overlapping scales and long spines, a living fortress that scuttled slowly across the sea bottom, feeding on microbial mats. And Morella, a delicate arthropod with ornate spines and feathery limbs, sometimes called the lace crab of the Cambrian. These creatures remind us that evolution's early attempts were not always about speed or ferocity. Defense, disguise, and niche specialization all had their place. But amid the oddities, something profound was stirring. In these same oceans lived the first chordates, small, fish-like animals with primitive backbones. Among them was Pikaia, a slender creature that swam with an undulating motion. Though it might have looked insignificant compared to armored trilobites or predatory Anomalocaris, Pikaia represents the earliest known ancestor of vertebrates, the lineage that would one day give rise to fish, amphibians, reptiles, birds, and mammals, including us. The Cambrian seas were a crucible, a place where evolution tested nearly every imaginable blueprint. Some designs failed and vanished forever. Others endured, refined over millions of years, into forms we still recognize today. What unites them all is the sense of sudden, explosive innovation, as if life itself had shifted into overdrive. By the end of the Cambrian, the oceans were alive with predators, prey, and ecosystems of astonishing complexity. The stage was now set for the next great act in life's story, the rise of more structured food webs, and the steady march toward conquering the land. As the Cambrian period unfolded, the oceans grew increasingly intricate. No longer were they dominated by a handful of experimental organisms. Now they swarmed with trilobites in countless forms, worm-like burrowers that churned the seabed, spiny grazers, and swift predators slicing through the water. For the first time in Earth's history, food webs reached multiple levels, from producers that captured sunlight to grazers to apex hunters ruling the seas. Trilobites in particular came to symbolize this new age. These armored arthropods thrived across the globe, from shallow reefs to deeper waters, adapting into hundreds of species. Their faceted compound eyes were among the most advanced sensory organs of the time, giving them vision that surpassed nearly every other creature around them. For nearly 270 million years, trilobites would remain one of Earth's most successful lineages, a reminder of the enduring impact of Cambrian innovations. But the Cambrian was not only about the rise of predators and defenses. It was about the invention of complexity itself. Muscles, nervous systems, circulatory systems, and sensory organs all appeared in recognizable form for the first time. The basic body plans that define life today, from worms and insects to mollusks and vertebrates, can trace their ancestry to this single explosion of diversity. In many ways, the Cambrians set the rules of the evolutionary game. And yet, as dazzling as this period was, it was only the beginning. Toward the close of the Cambrian, Earth underwent shifts in climate and sea levels. Glaciations gripped the planet, lowering oceans and stressing ecosystems. Some lineages disappeared, while others adapted, preparing to thrive in what came next. What followed was not a collapse, but a transition. The Cambrians' evolutionary fireworks had opened the door to endless possibilities. And in the next period, the Ordovician, those possibilities would be realized in spectacular fashion. Life would diversify even further, spreading into every corner of the seas, constructing reefs, building vast ecosystems, and expanding the complexity of marine communities to an entirely new level. The Cambrian explosion remains one of the most extraordinary chapters in Earth's story, a moment when evolution seemed to accelerate beyond comprehension. It was here that the blueprint of modern life was drafted, tested, and refined. And it was here that the foundations were laid for the great dramas to come. The colonization of land, the rise of forests, the appearance of giant predators, and eventually, the world the dinosaurs would inherit. The curtain was about to rise on the Ordovician period, and with it, the seas would teem with life more abundant and more complex than ever before. Roughly 485 million years ago, the Earth entered the Ordovician period, a time when the oceans exploded with life in ways the Cambrian had only hinted at. If the Cambrian was evolution's grand opening act, the Ordovician was the full orchestra, swelling with richness, complexity, and scale. The shallow seas of this era were crowded with new forms. Trilobites still thrived in great numbers, scuttling across the ocean floor, but they were no longer alone. Brachiopods multiplied into endless varieties, carpeting reefs and seabeds with their shell-covered colonies. Bryozoans, colonial filter feeders resembling delicate lace, joined them, creating intricate underwater communities. Together, these creatures transformed seafloors into bustling metropolises, ecosystems as dense and interwoven as modern coral reefs. For the first time, animals built true reefs, massive structures that rose like underwater mountains. Composed of early corals and sponges, these reefs became havens for countless species, offering shelter, feeding grounds, and nurseries for marine life. Schools of armored fish without jaws swam in the open waters, while strange starfish-like echinoderms sprawled across the seabed, their arms stretching outward in search of prey. This was also the age when jawless fish, the earliest vertebrates, began to multiply. were small, armored with bony plates, and clumsy by later standards, but they represented the humble beginning of a lineage that would one day dominate the seas, the land, and even the air. For now, they were little more than footnotes in a marine world still ruled by invertebrates. Above the seabed, cephalopods, ancestors of squid and octopuses, emerged as the first great predators of the open ocean. Some were modest in size, no larger than a modern cuttlefish. Others grew into giants, stretching several meters long, their conical shells tapering to sharp points. Armed with tentacles and sharp beaks, they hunted trilobites, fish, and nearly anything smaller that crossed their path. These cephalopods were the apex predators of their time, unmatched in speed, intelligence, and precision. The Ordovician was not only about abundance, it was about innovation. Filter feeding, burrowing, predation, and grazing all expanded into new niches. The result was an ecological web that rivaled anything the planet had seen before. But the Ordovician world was also fragile. Its richness depended on high sea levels and warm, stable climates. Beneath the surface of its abundance, Earth's forces were already shifting. Continental drift, climate change, and looming glaciations would soon test this thriving marine Eden. For now, however, the Ordovician seas represented a triumph of evolution, an underwater paradise, teeming with creatures that filled every available niche, laying the groundwork for ecosystems that would echo throughout the rest of life's history. Beneath the shadow of giant cephalopods and vast reefs, another revolution was quietly taking place. It did not begin with dominance or abundance, but with small, unassuming fish, creatures only a few inches long, their bodies encased in bony armor. These were the ostracoderms, the first true vertebrates to spread widely through the oceans. At first glance, they may not have looked impressive. Slow swimmers, jawless, and clumsy, they fed by sucking in mud and filtering tiny particles of food. Yet in their humble frames lay the blueprint of a dynasty that would one day conquer every environment on Earth. The armor that encased their bodies was both protection and prison. It shielded them from predators, but also weighed them down. Mobility was limited, forcing them to stay near the seabed. Still, ostracoderms represented a leap forward. For the first time, vertebrates experimented with a skeleton, a backbone that supported muscles and movement in new ways. Though primitive, this structure opened possibilities no invertebrate could match. With each generation, natural selection refined their designs. Some developed better fins for stability, others lighter armor for quicker movement. The stage was set for a future breakthrough, jaws, that would transform vertebrates into some of the most formidable predators in history. Around them, invertebrates still reigned supreme. Trilobites scuttled in great herds, while corals and sponges formed reef walls that stretched for miles. Brachiopods crowded every surface, their shells filtering nutrients from the water. Above, cephalopods patrolled the open seas, their long tentacles sweeping through schools of smaller animals. The armored fish were, for now, background players, overlooked in a world dominated by giants and hunters. Yet time and evolution are patient. While trilobites would one day fade into extinction, the vertebrates would endure. In these first awkward armored swimmers lay the seeds of sharks, amphibians, reptiles, mammals, and eventually humans. To watch an ostracoderm moving sluggishly through the Ordovician seabed is to glimpse the very beginning of our own story, The Ordovician seas may have dazzled with their abundance of shells, corals, and tentacled predators, but history would remember these small, armored pioneers as the first sparks of a lineage that would eventually reshape the planet. The Ordovician period was not only an age of abundance, it was the time when ecosystems began to acquire the structure and sophistication we recognize today. In the warm, shallow seas that covered much of the planet, the first great reef systems rose from the seafloor. Built primarily by corals and sponges, they formed vast walls and ridges, stretching for miles like submerged fortresses of stone and life. These reefs were more than static structures. They were living cities, home to countless species that found shelter within their crevices. Trilobites nestled in hidden cracks to avoid predators. Worms burrowed deep into the limestone foundations. Brachiopods and bryozoans attached themselves to reef surfaces, filtering microscopic food from the passing currents. Above, cephalopods drifted like silent sentinels, their long shells gleaming in the light as they patrolled the reef edges for prey. Every level of life had a place. Grazers scoured microbial mats and algae that clung to surfaces. Filter feeders drew nourishment from the nutrient-rich waters. Predators hunted both on the seabed and in the open ocean. For the first time, ecosystems displayed the full hierarchy of producers, consumers, and top predators, tightly interwoven in delicate balance. It was in the reefs that specialization flourished. Some trilobites evolved spines for defense, while others developed streamlined bodies for speed. Certain species of echinoderms, relatives of starfish and sea urchins, extended long jointed arms into the currents, capturing plankton like nets. Nautiloid cephalopods honed their tentacles into deadly tools, able to seize prey with precision. Each adaptation fed into the complex machinery of life, shaping a system as dynamic and interactive as any coral reef today. The reefs also reshaped the oceans themselves. By stabilizing sediments and altering water flow, they created new habitats and microenvironments. Tiny organisms thrived in these sheltered spaces, contributing to nutrient cycles that enriched the seas further. In effect, life was not only adapting to its environment, it was engineering it, building structures that would change the chemistry and dynamics of entire ecosystems. Seen from above, an Ordovician reef would have looked dazzling, a multicolored sprawl of shells, corals, sponges, and swarms of swimming creatures, as vibrant as any tropical reef in the modern world. And yet all of it was new. Only 100 million years earlier, the seas had been nearly empty. Now they teemed with complexity, a testament to the rapid power of evolution. But the stability of these reefs and the flourishing life around them rested on fragile foundations. Earth's climate, oceans, and continents were constantly in motion. The forces that had nurtured this marine Eden could just as easily destroy it. And as the Ordovician marched forward, those forces began to shift. For tens of millions of years, the Ordovician seas thrived, overflowing with life more abundant than anything Earth had ever seen. But the stability that allowed such richness was only an illusion. Beneath the surface of this thriving world, the planet was in motion, its continents drifting, its climate shifting, its balance precarious. At this time, most of Earth's land masses were gathered in the southern hemisphere, slowly converging toward the South Pole. As these continents moved, ocean currents shifted, altering the distribution of heat and nutrients across the globe. What had been warm, shallow seas the cradle of reefs and marine diversity, began to change as ice sheets formed over polar regions. The Earth's climate cooled dramatically. Glaciers expanded, locking away vast amounts of water and causing sea levels to plummet. Coastal reefs that had once flourished in shallow waters were suddenly exposed, drying and dying under the open air. Vast stretches of seafloor, once home to thriving communities of trilobites, brachiopods, and corals, became barren deserts of rock. In the oceans that remained, life faced new challenges. Colder waters reduced the productivity of plankton, cutting food supplies at the very base of the food chain. Species adapted to warm, stable environments struggled to survive. Some managed to retreat to equatorial refuges, clinging to existence in shrinking pockets of suitable habitat. Others had no such escape. The slow-motion catastrophe that unfolded was Earth's first great mass extinction, the Late Ordovician event. Over the course of several million years, nearly 85% of marine species vanished. Entire lineages that had dominated the seas since the Cambrian were erased. Trilobites, once numbering in thousands of species, were decimated. Reef builders collapsed, leaving behind oceans stripped of their architectural wonders. And yet, mass extinctions are never simple stories of loss. They are also stories of opportunity. As ecosystems collapsed, niches opened for the survivors. Some lineages of brachiopods and mollusks weathered the storm, poised to diversify again once conditions stabilized. The armored, jawless fish, though reduced in number, persisted, quietly carrying forward the vertebrate legacy. Even trilobites, though battered, would continue into the next era, though never again in their former glory. The Ordovician ended not with a bang, but with silence. Reefs gone, populations thinned, oceans emptied of much of their richness. It was a sobering reminder of Earth's fragility and of how quickly abundance could give way to devastation. But as the planet warmed again and glaciers retreated, life began its slow recovery. From the wreckage of extinction, new chapters were ready to unfold. When the glaciers finally receded and sea levels rose again, the world that emerged was forever changed. The Ordovician reefs were gone, their vast coral and sponge cities reduced to rubble. The once thriving communities of trilobites, brachiopods, and cephalopods had been thinned, their diversity slashed by the cold grip of extinction. It was as if the oceans had been emptied, stripped of much of their wonder. And yet, in that silence, the survivors began to adapt. Among the greatest losers were the reef builders. Their collapse left the oceans without the sprawling habitats that had supported entire ecosystems. Without reefs, biodiversity temporarily shrank, forcing many species into new niches or driving them toward extinction. But in the long run, this collapse set the stage for new reef systems, built not just by corals, but by different groups that would rise in later ages. Trilobites, once the kings of the seafloor, never fully recovered. Though some lineages clung on, their golden age was over. Their decline opened space for other arthropods to diversify, paving the way for new evolutionary experiments. The armored, jawless fish, humble as they seemed, endured the extinction with surprising resilience. Protected by their bony plates and able to exploit muddy seabeds, they carried on in reduced numbers. These small survivors were not dominant, but they represented persistence. A steady thread of vertebrate evolution that would soon weave into something far greater. Cephalopods, too, endured. Though their reign as apex predators was briefly dimmed, their survival ensured that intelligence, speed, and precision would remain powerful tools in the evolutionary arsenal. In time, their descendants would rise again, taking on new forms that echoed through future oceans. What the Ordovician extinction truly revealed was life's paradox: fragility and resilience intertwined. Catastrophe had swept away most of what had flourished, but in doing so, it reshaped the evolutionary landscape. New opportunities emerged, and the survivors were poised to take advantage. Extinction, though devastating, had cleared the stage for innovation. As the Silurian period dawned, Earth's climate stabilized once more. Seas rose, flooding continental shelves and creating shallow marine environments where life could rebound. Forests of algae spread, reefs slowly began to reappear, and survivors of the crisis began their next chapter of diversification. The Ordovician seas had dazzled with abundance and then collapsed in ruin. But from their ashes came the promise of renewal. Life had faced its first great test, a mass extinction on a planetary scale, and proved that it could endure. The story was far from over. In the Silurian, new experiments awaited. Armored fish gaining dominance, arthropods venturing onto land, and ecosystems rebuilding in bold, unexpected ways. Roughly 443 million years ago, the Earth entered the Silurian period. The scars of the Ordovician extinction were still fresh. Entire lineages were gone, ecosystems shattered. Yet, as the climate stabilized and glaciers retreated, the oceans once again filled with possibility. Where silence had reigned, life returned with quiet determination. In the shallow seas, reefs began to rebuild. Unlike the vast coral sponge fortresses of the Ordovician, these new reefs were constructed by different architects: tabulate and rugose corals, working together with stromatoporoid sponges. Slowly, they pieced together underwater cities, rising from the rubble of extinction. These reefs provided shelter for countless species, from small mollusks and worms to trilobites and brachiopods struggling to reclaim their former abundance. Among the most remarkable survivors were the cephalopods. Though diminished, they adapted swiftly to the new world. Some grew into coiled forms, the first nautilus-like shells curving elegantly instead of stretching straight into the depths. These coiled shells gave their owners better buoyancy and control, advantages that would ensure their continued role as apex predators of the seas. But the true stars of the Silurian recovery were the fishes, the armored jawless ostracoderms, survivors of the extinction, diversified into new shapes and sizes. They dominated river mouths and shallow waters, their bony plates shining like shields. And then came something entirely new: the first fish with jaws. Known as placoderms, they were small at first, their mouths lined with primitive biting plates instead of teeth. Yet this simple innovation changed everything. With jaws, fish could grasp, crush, and slice their prey. Feeding no longer meant sifting mud or filtering water. It meant active hunting. This single adaptation set vertebrates on a path toward dominance. In time, jawed fish would grow larger, faster, and more complex. But in the Silurian, they were still humble pioneers, testing the waters of their evolutionary potential. Meanwhile, the first hints of a world beyond the oceans were beginning to appear. Along coastal margins, simple plants resembling mosses and liverworts began to creep onto damp soils. They Their tiny green mats clung to shorelines, stabilizing sediments and capturing sunlight in a way no organism on land had ever done before. Soon, they would transform the planet's atmosphere and landscapes, paving the way for animals to follow. The Silurian was not as explosive as the Cambrian or as rich as the Ordovician, but it was a period of renewal, of slow rebuilding after disaster. It was a time of first steps, fish learning to bite, plants learning to root, ecosystems learning to recover. And with every innovation, life expanded its reach, preparing for revolutions still to come. The Silurian seas were steadily recovering, but this was not a simple return to the past. The ecosystems that rose from extinction were new, filled with evolutionary breakthroughs that would shape the future of life on Earth. Chief among these innovations was the rise of fish with jaws, a transformation that redefined what it meant to be a predator. Placoderms, the first true-jawed fish, appeared in the Silurian seas as small, heavily armored hunters. Their bodies were encased in bony plates, their mouths lined with sharp edges capable of slicing through prey. While many were modest in size, perhaps only a foot or two long, they represented a leap forward in design. Unlike their jawless predecessors, they were active, aggressive, and efficient. For the first time, vertebrates could truly dominate the hunt. These early jawed fish coexisted with the older ostracoderms, who remained slow, armored bottom feeders. But the balance was shifting. In the long march of evolution, the ostracoderms were a fading chapter, while placoderms were a bold new beginning. Their descendants would give rise to sharks, rays, and bony fish, the ancestors of nearly all vertebrates alive today. While fish experimented with armor and jaws, the reefs of the Silurian surged with growth. Tabulate and rugose corals expanded across shallow seas, their colonies interlocking to form structures that dwarfed anything in the Ordovician. These reefs became strongholds of biodiversity, buzzing with trilobites, mollusks, and echinoderms. Crinoids, relatives of starfish, anchored themselves in vast fields, their feathery arms reaching upward like meadows under the waves. And yet, the most significant story of the Silurian may not have been in the oceans at all. Along the margins of coasts, something remarkable was happening. Simple green plants, no taller than a few inches, were spreading inland. They had no roots, no wood, no flowers, but they were the pioneers of the terrestrial world. With each generation, they captured more sunlight, produced more oxygen, and stabilized more soil. Their silent conquest marked the first true greening of Earth's barren continents. Not far behind them came the arthropods. Millipede-like creatures, armored in segments, ventured onto the damp shorelines. Scorpions, still tied to water, crept onto land for brief moments, exploring the edge of a new frontier. These tentative forays were the first footsteps in a story that would eventually lead to fully terrestrial ecosystems, forests, and the rise of land-dwelling vertebrates. The Silurian world was balanced between recovery and revolution. In the seas, jaws and reefs transformed life. On land, plants and arthropods were rewriting the rules of survival. The stage was being set for an even greater leap, the colonization of Earth's continents. The Silurian period, lasting from about 443 to 419 million years ago, was an age of quiet strength. Compared to the upheavals of the Ordovician, this was a time of relative stability. The climate warmed, the glaciers that had once covered vast areas retreated, and sea levels rose once more, flooding the continents with shallow seas that teemed with recovering life. Unlike earlier ages, the Silurian did not bring dramatic extinctions or sudden bursts of novelty. Instead, it was a period of consolidation, of ecosystems strengthening and diversifying within the framework established after the Ordovician crisis. Reefs expanded and matured, corals and sponges building larger and more complex structures than ever before. These reefs were the lungs of the ocean, producing oxygen, sheltering fish, and serving as the centerpieces of rich marine communities. On land, the transformation was equally steady, but no less profound. The first vascular plants appeared, armed with internal systems to transport water and nutrients. Unlike their moss-like predecessors, these pioneers could grow taller and spread farther inland. Still no higher than a few feet, they began to form the earliest proto-forests along the edges of rivers and wetlands. For the first time, patches of green began to break the monotony of Earth's barren continents, changing not only landscapes, but also the atmosphere itself. Each plant that photosynthesized added oxygen to the air, nudging the planet toward conditions that would one day support larger land animals. The arthropods that followed these plants became the first terrestrial animals. Millipede-like detritivores grazed on decaying plant matter, while early arachnids, perhaps the ancestors of spiders and scorpions, prowled the shorelines. Though still tethered to water for reproduction, they were testing the possibilities of a land-based existence. The age of insects and terrestrial predators was still millions of years away, but the groundwork had been laid. Meanwhile, the continents themselves were on the move. Most of Earth's land masses drifted closer together, inching toward future collisions that would form the supercontinent Euramerica. These shifting plates reshaped ocean currents, influenced climates, and altered the distribution of life. Where shallow seas spread across continental shelves, biodiversity flourished. Where land rose, rivers and lakes created new habitats for pioneering plants and fish. The Silurians' gift was not spectacle, but preparation. It healed the wounds of the Ordovician extinction, stabilized ecosystems, and planted the seeds, quite literally, for revolutions to come. The oceans were now filled with armored and jawed fish, the reefs stronger than ever, and the continents no longer lifeless wastelands, but budding landscapes of green. The next act in life's story would not be a quiet one. In the Devonian, often called the Age of Fishes, vertebrates would explode in size and diversity. Plants would conquer the land and forests, and the first true tetrapods would crawl from the water to begin an entirely new chapter of existence. By the close of the Silurian, Earth had changed in subtle but profound ways. What began as a recovery from mass extinction ended as a world poised for transformation. The seas, once emptied, now teemed with armored fish, agile cephalopods, and thriving reefs that stretched across the continents. The land, long barren, bore its first hints of greenery. Low mats of plants creeping farther from shore, binding soil and anchoring themselves against the elements. The oxygen levels in the atmosphere, once suffocatingly low, began to climb again thanks to these early plants. Though still not high enough to support large animals on land, the trend was set in motion. With each passing million years, Earth's skies grew more breathable, paving the way for terrestrial ecosystems that would one day rival the oceans in complexity. The animals that explored these proto-landscapes were small and tentative. Millipede-like arthropods crawled over damp soils, feeding on decaying plant matter. Some of the earliest scorpions may have ventured onto land as well, though they still returned to the water to reproduce. These pioneers were fragile, their presence fleeting compared to the permanence of the seas. But their journeys marked the beginning of a revolution that would forever reshape the continents. Beneath the waves, vertebrates were refining their craft. Placoderms grew larger and more diverse, their armored bodies filling roles from ambush predators to open water hunters. Sharks, still in their infancy, began to appear as lean, cartilaginous fish that would one day rival and outlast the placoderms themselves. The story of Jaws, an innovation only recently born, was already rewriting the balance of marine life. The Silurian was a bridge, a period of healing and preparation. It lacked the explosive experimentation of the Cambrian or the dazzling abundance of the Ordovician, but its contributions were no less vital. It gave vertebrates jaws, it gave land its first plants and animals, and it stabilized ecosystems in the wake of catastrophe. What lay ahead was not quiet consolidation, but another surge of change. The Devonian period, often called the Age of Fishes, would see vertebrates rise to new heights of power and diversity. Forests would begin to climb skyward, reshaping the atmosphere and the planet's surface. And in shallow swamps and estuaries, a new kind of creature would emerge. Vertebrates with limbs strong enough to bear their weight, ready to step onto land and begin one of life's boldest experiments. The Silurian had written the prologue. The Devonian was ready to open the next great act. About 419 million years ago, Earth entered the Devonian period, an age that would forever alter the course of life. Known as the Age of Fishes, this era saw vertebrates burst into dominance in ways the Silurian had only hinted at. The oceans brimmed with armored placoderms, nimble sharks, and schools of bony fish, each refining new strategies for survival. The seas of the Devonian were warm and shallow, stretching across continental shelves and inland seas. These environments became laboratories of evolution, where vertebrates expanded into forms both strange and powerful. Placoderms, the armored titans of their age, grew to monstrous sizes. The most formidable of them all was Dunkleosteus, a predator that could reach lengths of 30 feet, its jaws lined not with teeth, but with bony plates as sharp as blades. With a single bite, Dunkleosteus could shear through armor, crushing prey in an instant. It was one of the first true apex predators among vertebrates, a terror that ruled the oceans with brute force. Yet placoderms were only one side of the story. Sharks, descendants of simpler Silurian ancestors, began to diversify. Unlike their heavily armored rivals, sharks were sleek, cartilaginous, and fast. Though smaller in size, their agility gave them an edge. They were hunters built not for brute strength, but for precision and endurance. While placoderms would one day vanish, sharks would endure, refining their design through hundreds of millions of years to remain apex predators even today. Alongside them appeared the first true bony fish. These pioneers split into two great lineages: ray-finned fish, ancestors of the majority of fish alive today, and lobe-finned fish, a less numerous group, but one destined for greatness. Lobe fins were different. Their fins were supported by strong, fleshy bones, precursors of limbs that could bear weight. While most swam as ordinary fish, a few began to explore shallow waters, testing the boundaries between sea and land. The Devonian oceans were dynamic ecosystems, where predators, grazers and scavengers interacted in a delicate balance. Coral reefs, stronger and more extensive than ever before, provided havens for smaller creatures. Crinoids waved their feathery arms, filtering plankton from currents. Trilobites, though past their prime, still scuttled across sea floors, hunted by the growing ranks of fish. Every niche was filled, every role occupied, as life reached a new pinnacle of diversity. But the Devonian was not just in an age of underwater dominance. Beyond the shores, another transformation was quietly underway, one that would change the very face of the continents. Plants, once confined to small low mats, began to rise upward, reaching for the sky, altering both the landscape and the atmosphere. Forests were about to take root, reshaping the world forever. While the seas of the Devonian thundered with armored fish and agile sharks, a quieter but equally transformative revolution was taking place on land. Plants, once limited to low mats clinging to shorelines, began to evolve new strategies for growth. They developed vascular systems, networks of tubes that carried water and nutrients through their stems, allowing them to grow taller, sturdier, and more complex. By the Middle Devonian, plants had colonized wide swaths of damp lowlands. Towering over their smaller ancestors were the first tree-like plants, such as Archaeopteris. These giants could reach heights of 30 feet, with woody trunks and branches that spread into leafy canopies. They were not true trees in the modern sense, lacking flowers and seeds, but they were the pioneers of forests, reshaping entire landscapes. Forests did more than change the scenery. They transformed the very chemistry of the planet. Through photosynthesis, these plants pumped vast amounts of oxygen into the atmosphere while drawing down carbon dioxide. As forests spread, global temperatures cooled, and the balance of Earth's climate shifted. Soil, once bare and eroded by rain, became anchored by roots. Rivers changed their courses, carving stable channels through green valleys. The continents, long barren, began to take on the outlines of living worlds. The impact on life was immense. The oxygen-rich air created conditions that would one day allow animals to thrive on land. The shaded forest floors provided new habitats for insects and arthropods, who found food among decaying leaves and shelter under roots. Insects began to diversify rapidly, with primitive forms of springtails and early wingless species creeping across the ground. Some grew to impressive sizes, their bodies supported by the denser oxygen levels that plants continually enriched. But the forests were not only havens, they were also engines of change. As vast quantities of plant matter accumulated, much of it fell into swamps and bogs, where it decayed slowly, locking away carbon for millions of years. This process would have long-term consequences, driving glaciations and altering the trajectory of Earth's climate in ways that future ecosystems would feel for ages. The Devonian continents, once barren and lifeless, now stood transformed. Along rivers and coasts, forests of towering plants swayed in the wind, their roots gripping the soil, their branches spreading shade. Among them scuttled arthropods, the first animals to truly make land their own. The world was becoming greener, richer, and more complex. And in the shallow margins where forests met seas, vertebrates, those bold, lobe-finned fish, were beginning to test their limits. In swamps and lagoons, some of them were experimenting with lungs and stronger fins, pushing closer and closer to the greatest leap life had ever attempted, leaving the water behind. The Devonian swamps were crucibles of innovation. In In their murky waters swam lobe-finned fish with broad, fleshy fins supported by bones that resembled primitive limbs. Unlike ray-finned fish, which relied on delicate spines for movement, these creatures could push themselves along the bottom, navigating shallow streams and stagnant pools where agility mattered more than speed. One of the most famous of these pioneers was Tiktaalik. Discovered in rocks dating to around 375 million years ago, it was neither fully fish nor fully amphibian, but something in between. Its fins contained bones akin to wrists, allowing it to prop itself up in shallow water, or perhaps even haul its body briefly onto land. Its head was flat, its eyes positioned on top like a crocodile's, and it had both gills and lungs. Tiktaalik was not a land animal, but it was a step toward one, a transitional form that revealed how vertebrates were experimenting with life beyond the water. Soon, true tetrapods, four-limbed vertebrates, began to emerge. These early amphibian-like animals, such as Acanthostega and Ichthyostega, had digits on their limbs and could maneuver through swampy shallows. Though still bound to water for reproduction and survival, they represented a profound shift. Vertebrates had taken their first steps onto land. This move was more than symbolic. By leaving the water, tetrapods gained access to a new world filled with untapped resources, insects to eat, plants for shelter, and entire landscapes with little competition. It was a risky venture. Gravity, desiccation, and the lack of buoyancy presented constant challenges, but the rewards were enormous. Over time, descendants of these pioneers would spread across the continents, giving rise to amphibians, reptiles, birds, and mammals. The Devonian, then, was not just the age of fishes. It was the age when vertebrates began to imagine a world beyond the sea. Forests were spreading, insects were diversifying, and tetrapods were crawling from the swamps. Life was no longer confined to the oceans. It was staging an invasion of the land itself. But progress came at a cost. The Devonian world was not immune to disaster. As forests spread and climate shifted, ecosystems faced new pressures. Toward the end of the Devonian, Earth would be rocked by another wave of extinctions, striking hardest at the very creatures that had flourished so brilliantly. For tens of millions of years, the Devonian seemed unstoppable. Forests spread across continents. Fish diversified into forms both monstrous and elegant, and vertebrates ventured onto land for the first time. It was a triumph of innovation and expansion. Yet in deep time, no triumph lasts forever. The late Devonian would remind life, once again, of Earth's unforgiving cycles of creation and destruction. The causes of the Devonian extinction are still debated. Some scientists point to the spread of forests, whose deep roots broke down rock, releasing nutrients into rivers that poured into the seas. This nutrient flood may have fueled vast algal blooms, depleting oxygen and suffocating marine life. Others suspect massive volcanic eruptions, altering climates and poisoning oceans with ash and carbon dioxide. Whatever the trigger, the results were catastrophic. The extinction did not strike in a single blow, but unfolded in pulses over millions of years. Each wave cut deeper into ecosystems, dismantling the intricate webs that had flourished in Devonian seas. Coral reefs, which had reached extraordinary heights of complexity, collapsed entirely. For the next 100 million years, true reef systems would vanish from Earth, leaving oceans bare and ecosystems impoverished. The armored placoderms, once rulers of the seas, were among the hardest hit. Giants like Dunkleosteus, which had dominated with their crushing jaws, disappeared completely. Their extinction left a vacuum that would eventually be filled by sharks and bony fish, whose lighter, more adaptable bodies proved better suited to the shifting world. Trilobites, too, suffered yet another devastating blow, their diversity dwindling further toward eventual disappearance. On land, the crisis was less severe, but no less important. Many plant species endured, though forests may have receded under climatic pressures. The tetrapods, still fragile pioneers, teetered on the brink. Only a handful of lineages survived, but those survivors carried the potential to shape all terrestrial vertebrates to come. In total, the late Devonian extinction erased about 75% of all species. It was not the most dramatic of Earth's great die-offs, but it struck at the heart of the flourishing ecosystems that had defined the age of fishes. Entire dynasties collapsed, leaving survivors to navigate a changed world. And yet, as in every extinction, opportunity followed destruction. With the placoderms gone, sharks and bony fish surged into dominance. With reefs erased, new marine communities slowly rebuilt themselves in simpler forms. And with tetrapods clinging to survival, evolution preserved the blueprint for a terrestrial future that would transform the continents. The Devonian ended not with the quiet of stability, but with the silence of loss. But from that silence, life would rise again into the lush, swampy landscapes of the Carboniferous, where forests would tower higher than ever before, and new giants, both in water and air, would emerge. About 359 million years ago, Earth entered the Carboniferous period, a time when life pushed upward and outward like never before. This was the age of colossal forests, of dragonflies with wingspans as wide as hawks, of amphibians the size of crocodiles, and of ecosystems that seemed both familiar and utterly alien. The continents lay clustered near the equator, their climates warm and humid. Vast swamp forests stretched across the land, thick with towering lycophytes and horsetails, some reaching over 100 feet tall. These plants, primitive compared to modern trees, lacked flowers or seeds. They reproduced with spores, like giant mosses. Their trunks rose in dense groves, their roots spreading through the soggy earth, their leaves forming dark canopies that turned the world beneath into a damp twilight. In these shadowed forests, oxygen levels soared. Photosynthesis from the endless vegetation pumped so much oxygen into the air that its concentration rose to nearly 35%, far higher than today's 21%. This atmospheric shift reshaped life in extraordinary ways. Arthropods, their bodies limited in size by oxygen availability, grew to monstrous proportions. Dragonflies like Meganeura spread wings more than 2 feet across, dominating the skies as aerial predators. Millipedes like Arthropleura crawled across the forest floor, some stretching more than 8 feet long, their segmented bodies snaking through the undergrowth like armored trains. Giant scorpions and spiders stalked the shadows, predators of a world that seemed designed for nightmares. The swamps were not silent. Amphibians flourished in this lush environment, filling every niche from small insect eaters to massive hunters lurking in the water. Some, like Ariops, grew nearly 10 feet long, with sprawling bodies and toothy jaws, capable of seizing fish and unwary prey on land. They were the dominant vertebrates of the time, thriving in rivers, lakes, and wetlands. Yet despite their size, amphibians were still tethered to water. Their eggs lacked shells and dried quickly, binding them to swamps and wetlands where reproduction remained possible. Beneath the surface of ponds and rivers, fish still ruled. Sharks adapted into countless forms, from small-bottom dwellers to giants with spiral jaws. Ray-finned and lobe-finned fish swam in abundance, filling ecological roles left vacant by the Devonian extinction. The oceans, though simpler than before, remained fertile hunting grounds. But it was the forests that defined the Carboniferous. They were vast, alien, and teeming with life at scales unimaginable today. The swampy ground was thick with fallen logs and decaying vegetation, creating peat beds that would one day harden into coal, the very fuel that humans would burn hundreds of millions of years later to power their civilizations. This was Earth, transformed by plants, a world where oxygen itself sculpted giants, and where forests were both the architects and guardians of a new era of life. In the dark wetlands of the Carboniferous, amphibians reigned. Their hulking bodies sprawled across the forest floors and riverbanks, their calls echoing through the swamps. Yet for all their success, they carried a limitation that chained them to the water: their reproduction. Amphibian eggs were soft, jelly-like, and fragile. They had to be laid in water or moist environments, where they would desiccate and die. But evolution is relentless. Among the amphibians of the late Carboniferous, a new lineage began to emerge, one that would break free from this constraint. These were the first reptiles, and their innovation was as simple as it was revolutionary: the amniotic egg. Unlike the permeable eggs of their amphibian cousins, the amniotic egg was sealed within protective membranes and a leathery or hardened shell. Inside, it contained its own watery environment, a self-contained world that nourished and protected the developing embryo. For the first time, vertebrates no longer needed ponds or swamps to reproduce. They could lay their eggs on land, far from the dangers of aquatic predators and the instability of wetlands. This breakthrough transformed everything. Reptiles could colonize drier environments, expanding into uplands and forests where amphibians could not follow. Their young hatched as miniature versions of adults, ready to fend for themselves without undergoing the fragile tadpole stage. Reptiles were, in essence, the first truly terrestrial vertebrates. Early reptiles were small, lizard-like creatures scurrying among the roots of towering lycophytes. Some were insect eaters, snapping up the giant dragonflies and millipedes of the forests. Others evolved sharper teeth and stronger jaws, experimenting with carnivory. With time, they split into two great lineages: the synapsids, ancestors of mammals, and the sauropsids, ancestors of reptiles, birds, and dinosaurs. Though still modest in appearance, these humble pioneers carried the potential for entire future dynasties. Meanwhile, amphibians remained dominant in size and number, but the seeds of their decline had been planted. As reptiles spread, amphibians were increasingly confined to wet habitats. The invention of the amniotic egg meant that amphibians' ancient tie to the water would eventually limit their reign, while reptiles surged forward into new and harsher environments. The Carboniferous swamps thus became a turning point. In their damp shadows crawled not only giants like Arthropleura and dragonflies as wide as eagles, but also tiny reptiles whose eggs carried the future of life on land. From these inconspicuous creatures would spring the rulers of entire ages to come: the synapsid, mammal-like reptiles of the Permian, the dinosaurs of the Mesozoic, and eventually the mammals and humans of today. The forests had had given the world oxygen and fuel. Now, they had given birth to the very idea of terrestrial independence. The path was set, and Earth's story was about to grow more complex than ever. The Carboniferous world was a place both haunting and magnificent. Imagine stepping into one of its vast swamp forests, towering lycophytes rising like green skyscrapers, their trunks sheathed in bark-like tissue, their crowns exploding into spiky fronds. Beneath them grew horsetails and ferns, their leaves arching in dense clusters. The air was thick with humidity, rich in oxygen, and heavy with the scent of decay. Shafts of light pierced the canopy, illuminating a world alive with creatures that defied imagination. In the skies, dragonflies the size of hawks patrolled their territories. With wingspans stretching over 2 feet, Meganura hunted smaller insects with precision, their enormous compound eyes scanning every flicker of movement. These were the kings of the Carboniferous air, aerial predators unrivaled in their time. On the forest floor, the giant millipede Arthropleura crawled among fallen logs, its armored body stretching more than 8 feet long. Despite its fearsome appearance, this colossal arthropod likely fed on decaying plant matter, recycling nutrients through the ecosystem. Its sheer size was made possible by the high oxygen content of the atmosphere, which allowed arthropods to grow to scales unimaginable today. Lurking in the waterways were amphibian giants. Ariops, nearly 10 feet long, sat half submerged in the shallows, waiting to ambush unwary fish or smaller amphibians. With sprawling limbs and gaping jaws lined with sharp teeth, it was a formidable predator in its swampy domain. Other amphibians, smaller but numerous, filled niches ranging from insect hunters to aquatic grazers, creating a diverse mosaic of life within the wetlands. Every corner of the Carboniferous swamp was alive with sound. The rustling of massive arthropods in the undergrowth, the splash of amphibians diving into pools, the constant hum of insects in the air. Yet it was also a world of shadows. The dense canopy blocked much of the sunlight, casting the ground below into twilight. It was a landscape where sight was limited, but sound and smell ruled. These ecosystems were finely balanced. Plants built the forests, pumping oxygen into the air and locking away carbon in the form of peat. Animals thrived in the niches they created, arthropods in the skies and on the ground, amphibians in the swamps, reptiles scurrying quietly in the underbrush. But balance in Earth's history is always temporary. For all their richness, the Carboniferous ecosystems carried the seeds of their own collapse. As peat accumulated and oxygen soared, wildfires became more frequent, ripping through forests in sudden infernos. Climate shifts altered rainfall, destabilizing the swamps. And deep beneath the surface, tectonic forces were reshaping the continents, preparing the planet for upheavals yet to come. The Carboniferous was a paradise of giants, but like all paradises in Earth's story, it was fragile. Soon, the planet would turn, and its creatures would face trials unlike any before. For millions of years, the Carboniferous swamps had flourished, transforming Earth with towering forests, soaring oxygen levels, and sprawling wetlands teeming with life. But paradise, in deep time, is always fleeting. By the late Carboniferous, the forces of geology and climate were conspiring to unravel this lush empire. Continental drift was reshaping the planet. Vast land masses began colliding, slowly assembling into the supercontinent Pangaea. As mountains rose where continents collided, rainfall patterns shifted, and once humid lowlands grew drier. Swamps that had stretched across equatorial regions began to shrink, replaced by seasonally arid landscapes. The giant lycophyte trees, dependent on constant moisture, withered in the face of this new reality. Their dominance waned, and with them, the swamp forests that had defined the Carboniferous Age. The collapse of these forests carried sweeping consequences. The enormous amounts of oxygen they had pumped into the atmosphere began to dwindle. For the giant arthropods that had thrived in this oxygen-rich world, the decline was devastating. Meganeura, the dragonfly of hawk-like wings, and Arthropleura, the millipede longer than a man, both began to fade. Their size had been possible only under exceptional atmospheric conditions. As those conditions shifted, their reign came to an end. The amphibians, too, faced new challenges. Once, the dominant vertebrates of rivers and swamps, they found their habitats shrinking. Many species declined or disappeared, unable to adapt to drier environments. Yet, in this moment of loss, another lineage rose. Reptiles, with their amniotic eggs and scaly skin resistant to desiccation, were uniquely suited to the changing world. They spread into uplands and dry forests, areas amphibians could not conquer. Small and agile, they thrived where the giants faltered. Meanwhile, in the seas, sharks and bony fish diversified, continuing to fill ecological roles vacated by the extinction of the placoderms in the Devonian. The oceans remained vibrant, but they too felt the echo of climate shifts as falling sea levels and cooling waters reshaped marine communities. The late Carboniferous was a time of transition, from swamps to deserts, from amphibians to reptiles, from forests of lycophytes to new plant lineages better adapted to dryness. It was the closing act of a lush chapter in Earth's story, and the opening of another, harsher one. By the time the Carboniferous ended, the stage was set for the Permian period. On the vast, merging lands of Pangaea, new ecosystems would rise, filled with strange and formidable creatures. Amphibians would fade into the background, while reptiles, particularly the synapsids, the ancestors of mammals, would rise to dominance. The world of giant insects and endless swamps was gone. Ahead lay deserts, predators with saber-like teeth, and a new age of power and peril, the age of reptiles before the dinosaurs. The Carboniferous forests were more than ecosystems. They were engines of planetary change. Every fallen branch, every leaf that dropped into the swamps, every tree that toppled into the water, carried the seeds of Earth's distant future. Over millions of years, layer upon layer of plant matter piled up in the stagnant wetlands. Oxygen was plentiful, but decomposition was slow in the waterlogged soils. Instead of rotting away, the vegetation was buried, compressed, and preserved. In time, this organic material hardened into coal, vast seams stretching across what would one day become North America, Europe, and Asia. These ancient forests, long dead, would one day fuel the Industrial Revolution, powering human civilization with the energy of sunlight captured 300 million years earlier. In this way, the Carboniferous not only shaped its own age, but cast its influence across the entire history of life, reaching all the way to us. Imagine walking through these swamps, towering lycophyte trees with scaly trunks, some wider than a human house, their roots snaking across the muddy ground. Horsetails as tall as small buildings sprouted in dense stands, their hollow stems crackling in the wind. Ferns grew in thick carpets below, covering every patch of damp soil. It was saturated in green, layered with shadow and silence, broken only by the drone of insects and the heavy splash of amphibians returning to the water. The sheer scale of the forests made them ecological titans. They cooled the climate by locking away carbon dioxide, altered the chemistry of rivers with their roots, and transformed the air with oxygen. The world of the Carboniferous was not just inhabited by forests, it was ruled by them. And yet, these forests were also precarious. Their dominance depended on swampy lowlands and humid climates. As continental drift and climate shifts began to reshape Earth, their stability would falter. But for tens of millions of years, they stood as cathedrals of life, towering monuments of green that would never be seen again in such form. One of the most striking features of the Carboniferous was the sheer size of its arthropods. Insects and their relatives, freed from the oxygen limits that constrain them today, grew into giants that seem almost like creatures from a fantasy. Consider the dragonfly-like Meganeura. With wings stretching more than 2 feet across, it ruled the skies as an apex aerial predator. Its compound eyes, each with thousands of lenses, scanned the air for movement. Once prey was spotted, perhaps a smaller insect or even a juvenile amphibian, Meganeura swooped with a speed and precision unmatched, its spiny legs snapping shut like a living trap. To walk through a Carboniferous swamp was to live under the constant shadow of wings larger than a hawk's, each beat producing a low, unsettling hum. On the ground, Arthropleura crawled through the forests, a millipede longer than a man, stretching more than 8 feet. Its segmented body was armored with thick plates, and it moved with a slow, deliberate rhythm, hundreds of legs rippling in unison. Though herbivorous, feeding on ferns and decaying plant matter, its massive size made it a creature of awe and fear. Imagine sitting on a log, only to watch as a living wall of armored limbs slid past, indifferent to your presence. Giant scorpions and spiders added to the alien feel of the Carboniferous world. Some scorpions reached lengths of 3 feet, their claws snapping shut with deadly force. Spiders, though not yet evolved into their modern forms, were already experimenting with silk, weaving primitive snares across the undergrowth. Why did these giants exist only then? The answer lies in oxygen. The Carboniferous atmosphere contained far more of it than today, around 35% compared to our 21%. Arthropods breathe not with lungs, but through tiny tubes called tracheae that deliver oxygen directly to their tissues. In today's thinner air, their bodies are limited in size because oxygen can only diffuse so far. But in the oxygen-rich world of the Carboniferous, those limits were lifted, allowing insects and millipedes to grow to sizes impossible today. These creatures dominated their environments, filling roles that mammals, birds, and reptiles would later claim. They were the giants of the underworld, masters of air and soil, built not of bone, but of chitin. Their reign would end as oxygen levels fell in the late Carboniferous, but for millions of years, they embodied the alien majesty of a world ruled by forests and fueled by breath itself. Roughly 299 million years ago, the Carboniferous gave way to the Permian, an age of sweeping change. The swampy, oxygen-rich forests of the past were gone, replaced by drier landscapes and sprawling deserts. Pangaea, the great supercontinent, now stretched nearly pole to pole, its vast interior far from the stabilizing influence of the sea. This continental colossus created extreme climates, searing summers, freezing winters, and vast arid plains where only the hardiest plants and animals could survive. In this harsher world, new rulers emerged. Reptiles, no longer confined to damp swamps, spread across deserts, forests, and highlands. Among them, one lineage in particular began to dominate: the synapsids. These creatures were not reptiles in the modern sense, though they resembled them. They were a separate branch of amniotes, destined to give rise, much later, to mammals. But in the Permian, they were the masters of the land. One of the most iconic synapsids was Dimetrodon. Though often mistaken for a dinosaur, it lived nearly 100 million years before the first dinosaur appeared. Dimetrodon was a predator up to 12 feet long, with a sprawling body, powerful jaws lined with serrated teeth, and a distinctive sail rising from its back. The sail, formed by elongated spines, may have helped regulate body temperature or played a role in display, signaling strength to rivals or attracting mates. Whatever its purpose, the sail made Dimetrodon one of the most recognizable predators of the Permian. But synapsids were not limited to hunters. Herbivorous forms like a Dilophosaurus also carried sails on their backs, though smaller and studded with crossbars. Unlike Dimetrodon, the Dilophosaurus grazed on tough plants, its peg-like teeth and massive gut adapted for processing vegetation. Together, these two sail-backed synapsids, one a herbivore, the other a carnivore, exemplify the ecological diversity of their lineage. As the Permian unfolded, synapsids diversified further. Some evolved into stocky, barrel-bodied herbivores, armored against predators. Others became fleet-footed hunters with lighter builds and sharper teeth. In every corner of Pangaea, from deserts to forests, synapsids carved out their dominance, filling roles that reptiles and amphibians could not. Meanwhile, amphibians, once lords of the Carboniferous swamps, were reduced to smaller, specialized niches. Many retreated to rivers and lakes, overshadowed by their reptilian and synapsid cousins. In the oceans, new predators appeared as well. Sharks and bony fish continued to thrive, but marine reptiles and early amphibious tetrapods began testing the waters of dominance, setting the stage for future revolutions. The Permian was not a paradise of lush abundance like the Carboniferous. It was a land of struggle, where creatures evolved armor, sails, and teeth to survive in unforgiving environments. Yet in that crucible, life innovated endlessly, and the synapsids rose as the true rulers of the land, the precursors of all mammals to come. As the Permian period advanced, the synapsids grew ever more diverse, exploring forms both strange and powerful. Among them emerged one of the most fearsome groups of predators in Earth's history, the Gorgonopsids. These creatures looked like nothing alive today. Imagine an animal with the body of a muscular reptile, the stance of a sprawling mammal, and a head dominated by enormous saber-like teeth. Some Gorgonopsids grew as large as modern lions, their skulls elongated and armed with fangs that could pierce the thick hides of their prey. They were swift, agile, and lethal, the apex hunters of the late Permian. One of the most famous was an Austransevia, a predator that stretched over 10 feet long. Its saber teeth extended several inches, capable of delivering deep, devastating wounds. Unlike earlier synapsid predators such as Dimetrodon, which relied on brute strength, Gorgonopsids were built for efficiency. They combined speed, intelligence, and precision, striking with a power that few animals could withstand. The prey they hunted was was equally remarkable. Large herbivorous synapsids, like Dicynodonts, filled the Permian plains. These creatures had squat, barrel-shaped bodies and strong jaws, some equipped with tusks, and they grazed on tough, dry vegetation that had replaced the lush swamp plants of the Carboniferous. Herds of Dicynodonts roamed the arid landscapes of Pangaea, their numbers vast enough to sustain even the hungriest predators. It was a predator-prey arms race on a scale Earth had never seen before. Dicynodonts grew sturdier and more defensive, while Gorgonopsids grew sharper and more specialized. Each adaptation on one side drove innovation on the other, fueling an evolutionary contest that shaped the ecosystems of the late Permian. But the importance of Gorgonopsids goes beyond their ferocity. They reveal the direction in which evolution was steering the synapsids. Their legs were positioned more directly beneath their bodies than in earlier sprawling reptiles, hinting at the posture of mammals to come. Their skulls showed adaptations for powerful jaw muscles, and their teeth were differentiated into incisors, canines, and molars, a step closer to the specialized dentition of mammals. In the Gorgonopsids, we see not only terrifying predators, but also glimpses of traits that would echo in future mammalian lineages. The late Permian was their age, and they ruled it with deadly efficiency. But the story of the Permian is not only about triumph. Beyond the reign of the Gorgonopsids, a shadow was gathering. A catastrophe so profound it would erase nearly all of them, along with most of life on Earth. By the middle to late Permian, life on land had reached levels of diversity never before seen. Across the sprawling supercontinent of Pangaea, vast deserts stretched into the horizon, interrupted by pockets of forests and fertile floodplains. In these environments, the synapsids reigned supreme. Among the most successful herbivores were the Dicynodonts. These squat, tusked animals resembled a cross between a turtle and a pig, with powerful jaws and beak-like mouths that cropped tough plants. Their bodies were barrel-shaped, built for digesting fibrous vegetation, and they traveled in herds that could number in the hundreds. Though strange to modern eyes, Dicynodonts were incredibly resilient, surviving not only the harsh Permian climates, but also the great extinction that loomed ahead. Sharing the land with them were the Dinosaurs, bulky reptilian herbivores armored with bony plates and knobs across their skin. Some grew as large as modern hippos, lumbering through dry floodplains in search of plants. Despite their defensive armor, they often fell prey to Gorgonopsids, whose saber teeth could penetrate even the toughest hides. Predators and herbivores were locked in a perpetual contest, but the ecosystems of the Permian were more than battles between giants. Smaller synapsids scurried through the undergrowth, feeding on insects or seeds. Early reptiles diversified as well, adapting to niches from swift insect hunters to semi-aquatic fish eaters. Even amphibians, though no longer dominant, held on in rivers and lakes, some growing to enormous sizes. Their broad heads and sprawling bodies adapted to ambush hunting in murky waters. The oceans of the Permian were just as dynamic. Coral reefs rebuilt themselves after the Devonian collapse, teeming with sponges, mollusks, and brachiopods. Sharks diversified into bizarre shapes, some with whorled jaws like circular saws, others with long spines projecting from their heads. In deeper waters, strange ammonites, relatives of squid and octopuses, drifted with coiled shells, their tentacles probing the seas for prey. It was a world of innovation, but also of fragility. Pangaea's immense size meant extreme seasonal shifts, Inland regions baked under scorching summers and froze in bitter winters. Droughts and wildfires were frequent. Ecosystems flourished in the margins, along coasts, rivers, and wetlands. But vast stretches of land remained barren. The Permian world was one of extremes, where life thrived only through adaptation and resilience. Still, for tens of millions of years, these ecosystems endured. Herds of Dicynodonts roamed, Gorgonopsids hunted with saber jaws, and strange reptiles filled every available niche. It was a peak of diversity and dominance, the age of synapsids at its height. But Earth's history is punctuated by collapse, and as the Permian drew to its close, forces were gathering that would bring the greatest catastrophe life had ever faced. The late Permian world seemed rich and full of life, but beneath its surface, catastrophe was brewing. Geological forces were setting the stage for an extinction so profound that it would nearly erase life itself. In Siberia, immense volcanic eruptions began to tear open the Earth's crust. Over thousands of years, lava flooded across the land, covering an area larger than the continental United States. These eruptions, known as the Siberian Traps, released staggering amounts of gases into the atmosphere. Carbon dioxide surged, driving global temperatures upward. Methane, an even more potent greenhouse gas, may have been released from melting permafrost and seafloor deposits, amplifying the warming even further. The climate grew increasingly unstable. Summers became hotter, pushing ecosystems beyond their limits, while winters failed to provide relief. Rainfall patterns shifted, plunging many regions into drought. The once thriving forests of Pangaea withered, replaced by barren plains and deserts. Rivers dried up, lakes shrank, and fertile floodplains became dust. The oceans fared no better. As volcanic gases poured into the atmosphere, acid rain fell, poisoning soils and waterways. The seas absorbed vast amounts of carbon dioxide, turning acidic and hostile to shell-building organisms. Meanwhile, the warming climate disrupted ocean circulation, reducing the mixing of surface and deep waters. The result was anoxia, vast dead zones where oxygen vanished, suffocating marine life. Coral reefs, already fragile, collapsed. Mollusks, brachiopods, and ammonites dwindled. Even trilobites, survivors of multiple previous extinctions, began their final decline. On land, the effects were equally devastating. Gorgonopsids, once the apex predators of their age, struggled as their prey dwindled. Dicynodon herds diminished as plants died back. The food webs that had sustained Permian ecosystems unraveled, collapsing from the bottom up. Insects, which had flourished in carboniferous forests, suffered their first mass extinction, many lineages disappearing forever. Yet the devastation was not sudden. It unfolded over hundreds of thousands of years, wave after wave of ecological collapse hammering life across the globe. With each pulse, diversity thinned further, until only fragments of the once great Permian ecosystems remained. Still, there were survivors, small reptiles able to endure harsh climates, burrowing animals that escaped the worst of the heat, and hardy plants capable of weathering drought. But the age of great synapsids was ending. Their dominance would be shattered, leaving only a handful of lineages to stumble into the next era. The Permian had begun with triumph, a flourishing of life across continents and seas. But it was ending with fire, heat, and silence. The stage was set for the most devastating extinction event in Earth's history, the Great Dying. The Permian world was defined not just by its creatures, but by its landscapes. Unlike the swampy forests of the Carboniferous, Pangaea's vast supercontinent created extreme climates that tested life to its limits. Imagine standing in the middle of Pangaea's interior. The land stretches endlessly in all directions, a vast desert broken only by rocky ridges and the occasional oasis. Summers scorch the ground with relentless heat, while winters bring biting cold. Rainfall is scarce, and rivers flow only seasonally, turning into dry channels for much of the year. It is a world of extremes, but also one of extraordinary adaptations. Here, synapsids like the Dicynodonts gathered in herds near rivers and lakes. Their tusked jaws and sturdy bodies allowed them to graze on the tough plants that grew in patches of green. In the open deserts, Pariasaurs lumbered slowly, their armored hides glinting under the sun as protection against predators. Smaller reptiles scurried between rocks, avoiding the heat by seeking shade during the day and emerging at night to hunt insects. Predators thrived in this harsh world as well. Gorgonopsids prowled the edges of floodplains, their saber teeth gleaming as they stalked herds of herbivores. Some archosaur relatives, ancestors of crocodiles and dinosaurs, also began to experiment with new forms, hinting at the future rulers of the Mesozoic. Even amphibians, though diminished, survived in rivers and lakes, some growing to massive lengths, lurking in the water for prey. The deserts of the Permian were not empty wastelands. They were arenas of survival, where each adaptation, a sail for thermoregulation, armor for defense, tusks for grazing, saber teeth for killing, made the difference between life and death. Unlike the lush abundance of the Carboniferous, this was a world where every calorie, every drop of water, every breath of air was precious. And yet, life flourished. From the smallest burrowing reptiles to the great predators of the floodplains, Permian ecosystems were rich and varied, adapted perfectly to the challenges of their time. It was evolution under pressure, a crucible that produced innovations destined to echo through the ages. The Permian is often remembered for its catastrophic ending, but before the apocalypse, it was an age of dynasties, most of them led by the synapsids. These creatures, our distant ancestors, were endlessly inventive, filling nearly every ecological role on land. Take the Dicynodonts, for example. Though squat and strange-looking, they were remarkably successful. With their beaked mouths and tusks, they grazed on the dry, fibrous plants that grew across Pangaea's floodplains. Some species were small, scurrying close to the ground, while others grew to the size of modern cattle, moving in herds that shook the earth as they migrated from one patch of vegetation to another. Their ability to adapt to different climates and diets made them one of the most enduring synapsid groups. Then there were the Dinocephalians, a group whose very name means terrible heads. These bulky creatures had thick skulls, some with bony domes, and ridges used for combat. Males may have clashed head-to-head, like rams or bison, in battles for dominance. Some were herbivores, chewing through tough plants with massive jaws, while others were carnivores, towering predators with powerful teeth and claws. Though they would not survive the entire Permian, they marked a chapter of synapsid experimentation on a grand scale. Among the carnivores, the Gorgonopsids stood supreme. Their saber-like canines and agile bodies made them the apex hunters of the late Permian. Some species grew as large as lions, while others were small and lithe, darting after quick-moving prey. In In their mix of speed, endurance, and specialization, they represented the cutting edge of Permian evolution. But not all synapsids were giants. Many were small and nimble, filling niches similar to those of modern rodents, weasels, or foxes. These lesser-known species hunted insects, scavenged carrion, or fed on seeds and plants, weaving the complex web of Permian ecosystems. Their diversity ensured that synapsids were not just rulers of the land, they were its backbone. What makes the synapsids of the Permian so remarkable is how many of their traits foreshadow mammals. Differentiated teeth, stronger jaws, more upright postures, and even hints of warm-bloodedness appear in their fossils. They were not mammals, but the blueprint was forming. A story of adaptation that would eventually lead, through countless generations, to creatures like us. The Permian was their golden age. They ranged from herds of tusked grazers to saber-toothed predators, from dome-headed giants to scurrying insectivores. It was a world where synapsids were kings. But even dynasties must face their end, and the greatest test in Earth's history was drawing near. For tens of millions of years, the Permian world thrived. Synapsids ruled the plains and deserts, reptiles multiplied into new forms, and marine life rebounded after earlier extinctions. To a casual observer, it might have seemed as though this was the pinnacle of Earth's evolutionary story. But beneath the surface, the planet was growing unstable, and the warning signs were mounting. Climate was the first alarm. As Pangaea stretched nearly from pole to pole, its immense landmass created weather extremes unlike any seen before. Summers in the continental interior became unbearably hot, while winters plunged into freezing cold. Rain patterns shifted, leaving vast regions dry and barren. Forests and wetlands shrank, and deserts spread like scars across the land. Species that depended on stable habitats found themselves under increasing pressure. Volcanism also left its mark. In what is now Siberia, deep fissures in the Earth's crust began to awaken. At first, the eruptions were sporadic, but over time, they grew larger and more frequent. Great plumes of ash and gas darkened the skies, disrupting weather and poisoning soils. For animals and plants already struggling with climate extremes, these disturbances added new stresses. In the oceans, subtle but dangerous changes were underway. Coral reefs began to decline, and shallow seas grew more hostile. As volcanic activity released carbon dioxide, the oceans absorbed it, becoming more acidic. Shell-building organisms, from brachiopods to early corals, struggled to survive. Nutrient cycles faltered, and signs of oxygen depletion spread across the seafloor. Life, of course, adapted as best it could. Dicynodonts continued to graze, and predators like the gorgonopsids still prowled the floodplains. But ecosystems were less resilient than they had once been. Food webs grew fragile, dependent on fewer species. Each disruption sent ripples through the system, threatening collapse. In hindsight, the signs are clear. Ecosystems stretch thin, climates in flux, volcanism stirring beneath the ground, oceans losing their breath. The stage was being set for a catastrophe that would make all previous crises pale in comparison. And yet, for millions of years, life continued, unaware of the doom approaching. Herds grazed, predators hunted, and the great deserts of Pangaea echoed with the footfalls of synapsids. The world seemed alive and strong, but the foundation beneath it was crumbling. The final act of the Permian was about to begin, not with a whimper, but with fire. About 252 million years ago, the Permian world collapsed into ruin. What followed was the single most devastating extinction event in Earth's history, so severe that paleontologists simply call it the Great Dying. In a geologic blink, nearly 90% of marine species and 70% of terrestrial vertebrates vanished. Entire ecosystems disintegrated, leaving behind a world unrecognizable. The trigger was the relentless volcanism of the Siberian Traps. For hundreds of thousands of years, colossal eruptions poured lava across millions of square miles, releasing immense quantities of gases into the atmosphere. Carbon dioxide levels soared to unprecedented heights, driving a runaway greenhouse effect. Global temperatures spiked by as much as 18 degrees Fahrenheit, turning the planet into a furnace. The oceans became hostile wastelands. As the climate warmed, circulation currents slowed, and oxygen levels plummeted. Vast stretches of sea turned anoxic, their waters suffocating to fish, mollusks, and corals. Hydrogen sulfide, a poisonous gas, may have bubbled up from the depths, killing marine organisms and even drifting into the atmosphere to devastate land ecosystems. Coral reefs disappeared entirely, not to reappear in their modern form for tens of millions of years. Trilobites, after thriving for nearly 300 million years, went extinct forever. On land, the crisis was equally apocalyptic. Forests died, their soils eroded into dust, rivers dried to trickles, and wetlands vanished. Herbivores starved as vegetation withered, and predators followed in their wake. Even the mighty gorgonopsids, apex hunters of the late Permian, succumbed. Only smaller, more adaptable animals survived, such as certain burrowing reptiles and insect-eating synapsids that could endure the extremes. The very chemistry of the atmosphere shifted. With plants dying en masse, oxygen levels fell to some of the lowest in Earth's history, perhaps as little as 12% compared to today's 21%. For large animals, breathing became a struggle. The combination of heat, drought, toxic air, and collapsing food chains created an inescapable trap for most forms of life. To imagine the Great Dying is to imagine silence. The chorus of insects that once filled the forests was gone. The heavy footfalls of dicynodont herds faded into extinction. The roar of predators like Inostrancevia fell silent. Seas once vibrant with ammonites, trilobites, and fish became eerie voids. The Earth, once overflowing with diversity, was reduced to desolation. And yet, even in the face of catastrophe, life did not disappear entirely. A handful of survivors clung to existence, enduring in pockets of stability, waiting for the chance to rebuild. The Great Dying had torn down the world, but in its aftermath, it would also clear the way for something new. A transformed biosphere, and the rise of creatures that would inherit the next age. In the wake of the Great Dying, Earth was a planet of silence. Entire ecosystems had been erased, and the survivors clung to existence in landscapes stripped of complexity. It was not just a mass extinction, it was a reset, a collapse of life's intricate networks back to their barest foundations. For millions of years after the catastrophe, biodiversity remained shockingly low. Where once forests had stretched across Pangaea, now barren plains and sparse vegetation dominated. Rivers carried sediments into lifeless seas, where only scattered organisms endured. The planet had become an ecological desert. Among the few survivors were the dicynodonts, those tusked herbivores that had roamed Permian floodplains in vast herds. Though greatly reduced in diversity, some species endured. their sturdy bodies and flexible diets giving them an edge in a world where resources were scarce. They became the workhorses of the Triassic landscapes, holding on when so many others had vanished. Another lineage that endured was the cynodonts, small synapsids with features edging closer to mammals. Unlike their massive gorgonopsid cousins, cynodonts were adaptable, burrowing or living in small groups, feeding on insects and plants that still persisted. They carried traits that hinted at the mammalian future: differentiated teeth, more efficient jaws, and perhaps even whiskers or fur for insulation, and a climate prone to extremes. In the oceans, life was slow to recover. Coral reefs remained absent for tens of millions of years, leaving shallow seas barren of the vibrant communities they once supported. Ammonites, however, survived and began to diversify again, becoming one of the most important marine groups of the Triassic. Sharks and bony fish, too, endured, though in reduced numbers, slowly reclaiming the niches left vacant by the extinction. The aftermath of the Great Dying was not just a story of survival, but of transformation. The old Permian world, with its gorgonopsids, sail-backed predators, and swamp-dwelling amphibians, was gone forever. In its place, a new caste of creatures was rising, shaped by the harsh realities of post-extinction Earth. The Triassic landscapes that followed were strange and eerie. Where once herds of diverse synapsids roamed, now only a few resilient species lingered. Reptiles, which had been minor players in the Permian, began to expand into the empty niches. The stage was being reset, not for a return to what had been, but for the rise of something entirely new. The Great Dying had nearly ended life, but it also cleared the path for new rulers. In the shattered silence of the early Triassic, the seeds of the next great dynasty were sown. The dynasty of the reptiles that would one day give rise to the dinosaurs. The early Triassic, immediately after the Great Dying, was unlike any other time in Earth's history. The catastrophe had not only reduced life, it had destabilized the very systems that supported it. For millions of years, the planet remained locked in a hostile state. Global temperatures soared to extremes. Some estimates suggest equatorial regions reached sustained averages of 120 degrees Fahrenheit, creating vast belts of uninhabitable desert across the heart of Pangaea. Rainfall became erratic, with long droughts broken by sudden floods. The supercontinent's immense size meant that much of its interior lay far from the moderating influence of the oceans, amplifying the harshness of its climates. Oxygen levels in the atmosphere remained perilously low, perhaps around 12%. For large animals, simply breathing was a struggle. Some scientists compare it to living permanently on the summit of a high mountain. This scarcity of oxygen further limited recovery, preventing ecosystems from regaining their former richness. On land, survivors lived precariously. The cynodonts, once so diverse, dwindled to just a handful of species. They gathered in small groups on floodplains and near rivers, where vegetation still clung to life. Cynodonts scurried through the undergrowth, insect-hunting generalists that could survive on whatever scraps the environment provided. Reptiles, particularly archosaurs, the group that would one day include crocodiles, pterosaurs, and dinosaurs, began to expand, exploiting niches left vacant by vanished predators. In the oceans, conditions were equally grim. Large swaths of shallow seas remained stagnant and anoxic, hostile to most forms of life. Ammonites, though battered, began to multiply, slowly diversifying into new forms. Fish, too, crept back into prominence, but coral reefs, once the crown jewel of marine ecosystems, were gone, leaving the oceans eerily empty. The early Triassic is sometimes called Earth's disaster interval. It was not just a recovery period, but an age when ecosystems were stuck in low gear, unable to fully rebound. Extinction pressures remained high, and life existed at the edge of survival. For millions of years, Earth was a wounded planet, struggling to find balance again. Yet within this desolation, the seeds of new beginnings took root. Evolution thrives on opportunity, and though the Great Dying had erased much, it had also cleared vast ecological space. Those who endured, cynodonts, dicynodonts, archosaurs, and small reptiles, would form the foundation of a new era. Slowly, over millions of years, the Earth began to heal. By the Middle Triassic, climates stabilized somewhat, and ecosystems grew more robust. Vegetation spread again, with conifers, seed ferns, and other hardy plants taking hold on the floodplains and uplands of Pangaea. With more stable plant life, herbivores found new opportunities, and with herbivores came predators. The dicynodonts, though no longer diverse, remained resilient. Their squat bodies and tusked jaws made them successful grazers, and they spread across multiple continents, becoming a staple of Triassic ecosystems. Cynodonts diversified into a range of forms, from small insect eaters to larger omnivores and carnivores. Their advanced jaws and differentiated teeth gave them advantages in processing food, and their mammalian features grew more pronounced. But the greatest beneficiaries of the post-extinction world were the archosaurs. These reptiles, once minor players, now surged into dominance. Some evolved into crocodile-like hunters that patrolled rivers and wetlands. Others grew into agile, lightly built forms adapted for running across open plains. And among their ranks were the first small, lightly built creatures that would one day give rise to dinosaurs. In the oceans, ammonites diversified into new spirals and shapes, becoming the most abundant marine invertebrates of the Triassic. Early marine reptiles, like nothosaurs, began to appear, slipping between water and land with streamlined bodies and sharp teeth for catching fish. The seas were stirring back to life, even if they lacked the grandeur of earlier reefs. The Great Dying had ended the world of the Permian, but it also reset evolution. What survived was not a shadow of the past, but the foundation of the future. Life would never look the same again. The Triassic would be the age of recovery and reinvention. From the ashes of Earth's deadliest extinction, survivors would rise, adapt, and diversify. And among them, new dynasties would begin to form. Dynasties that would one day belong to the dinosaurs. Around 252 million years ago, in the aftermath of the Great Dying, Earth stood at its lowest point. Life had been nearly erased, and what remained was fragile, scattered, and subdued. Yet the story of the Triassic is not one of despair, but of renewal. Against impossible odds, the survivors of the extinction clawed their way back, and in doing so, they laid the foundations for one of the most extraordinary chapters in the history of life. At first, the Triassic world was strange and austere. Pangaea still dominated the globe, its vast deserts stretching for thousands of miles, its coasts lined with seasonal wetlands and forests of hardy conifers and seed ferns. The climate was harsh, hot, dry, and unpredictable. But gradually, Ecosystems stabilized. Plants grew more abundant, soils regenerated, and rivers carved out fertile plains. Slowly, diversity began to climb again. The animals that inherited this world were different from those that had ruled the Permian. Gone were the sail-backed predators, the gorgonopsids, and the massive pariasaurs. In their place rose the archosaurs, a lineage of reptiles whose adaptability would reshape the planet. Archosaurs were divided into two great branches, the crocodile line and the bird line. The crocodile line gave rise to armored predators and massive amphibious hunters, while the bird line included agile, lightly built reptiles that would eventually evolve into pterosaurs, dinosaurs, and birds. Yet synapsids, the ancient relatives of mammals, did not vanish. The cynodonts, small, fur-bearing insectivores and omnivores, thrived in shadows. With their advanced teeth, strong jaws, and likely warm-blooded metabolism, they were adaptable survivors, filling roles that reptiles could not. Some grew into larger predators, stalking the undergrowth with sharp canines, while others remained small, living in burrows and hunting at night. Though overshadowed by archosaurs, the cynodonts carried forward the spark of the mammalian future. The seas also began to stir with innovation. Ammonites flourished once again, their spiral shells drifting through the currents in dazzling abundance. Early marine reptiles like nothosaurs patrolled coastal waters, their long necks darting after fish. Soon, even stranger forms would appear. Streamlined ichthyosaurs, resembling dolphins, that would become the swiftest predators of the Triassic oceans. The early Triassic was a time of rebuilding, but by the Middle Triassic, life was not merely recovering, it was reinventing itself. New predators, new herbivores, and new ecosystems emerged, different from anything the world had seen before. And within this explosion of experimentation, a new dynasty was preparing its first tentative steps, the dinosaurs. By the Middle Triassic, some 10 million years after the Great Dying, Earth's ecosystems were stirring back to life. Recovery was slow, but it was relentless. The archosaurs, once obscure reptiles in the shadow of synapsids, now surged into dominance, taking over niches on land, in rivers, and even in the skies. On the ground, crocodile line archosaurs diversified into a remarkable array of predators. Some developed heavy armor and sprawling postures, resembling strange tank-like reptiles that ambushed prey from cover. Others evolved into swift, upright hunters with long legs, capable of pursuing herbivores across open plains. Their adaptability was unmatched, and in a world still rebuilding from extinction, it gave them the edge over their competitors. Herbivores, too, were evolving rapidly. Dicynodonts, those tusked synapsid grazers, remained abundant in many areas, their sturdy bodies crowding river valleys and floodplains. But alongside them rose new reptilian herbivores, such as the rhynchosaurs. With beak-like jaws and cheek teeth adapted for shearing vegetation, rhynchosaurs spread widely across Pangaea, thriving in environments where plants grew thick. In some regions, they made up the majority of large herbivore populations. Meanwhile, in the seas, reptiles were rewriting the rules of marine life. The nothosaurs, with their paddle-like limbs and long necks, darted after fish in shallow waters. From them evolved the plesiosaurs, whose graceful, four-flippered bodies would dominate the oceans for millions of years. Even more dramatic were the ichthyosaurs, streamlined, dolphin-like reptiles that became the fastest predators of their age. With massive eyes adapted for hunting in dim light, they They prowled coastal seas and open oceans alike, diving deep in pursuit of squid and fish. The ichthyosaurs were among the most successful of all Triassic survivors, heralding a new age of marine dominance. And then, quietly, almost unnoticeably, the first dinosaurs appeared. They were not the colossal beasts that would one day rule the Jurassic and Cretaceous. Instead, they were small, lightly built creatures, no taller than a human. One of the earliest was Eoraptor, a swift bipedal predator from South America. With grasping hands, sharp teeth, and long legs for running, it was agile but modest, living in the shadow of larger archosaurs. Another was Herrerasaurus, a slightly larger predator, perhaps 10 feet long, but still insignificant compared to the dominant reptiles of its time. At this stage, dinosaurs were merely one experiment among many. They were rare, restricted to certain corners of Pangaea, and far from the rulers they would one day become. Yet their traits, upright posture, speed, endurance, and adaptability, would give them the tools to outlast their rivals. The Triassic was a crucible, testing countless designs. Many would vanish, leaving little trace. But a few, including the small, unassuming dinosaurs, were destined to inherit the Earth. By the late Triassic, roughly 230 million years ago, Earth had transformed into a world bustling with new giants. The scars of the Great Dying were fading, and ecosystems were vibrant once more, filled with predators and herbivores that bore little resemblance to those of earlier ages. This was a time of experimentation, when evolution filled every available niche with strange and formidable creatures. Among the most imposing of the Triassic herbivores were the prosauropods, early relatives of the great long-necked sauropods that would later dominate the Jurassic. Plesiosaurus was one of the first of these giants, growing up to 30 feet long, with a long neck and sturdy body. It fed on the conifers and cycads that carpeted Triassic floodplains. Though primarily herbivorous, its flexible jaw and teeth suggest it may have been opportunistic, consuming small animals if needed. Herds of Plateosaurus browsed across the landscape, foreshadowing the colossal sauropods yet to come. But the herbivores were not unchallenged. The apex predators of the Triassic were not dinosaurs, but Rauisuchians, massive crocodile-like archosaurs that walked on powerful, upright legs. Some species grew over 20 feet long, with skulls packed with blade-like teeth. Unlike modern crocodiles, which sprawl low to the ground, Rauisuchians had erect postures, allowing them to move swiftly across land. They were the terror of their ecosystems, ambushing or chasing down even the largest herbivores. Smaller predators abounded as well. Early theropod dinosaurs, like Herrerasaurus and Coelophysis, hunted in packs or alone, preying on smaller reptiles and synapsids. While not yet the rulers of their ecosystems, these nimble hunters displayed the traits that would one day make dinosaurs so successful: speed, agility, and endurance. Synapsids still clung to survival. Cynodonts, the mammal-like reptiles, remained diverse, ranging from dog-sized carnivores to tiny insect eaters that may have been nocturnal. Some species show evidence of whisker pits and even hints of fur impressions, suggesting they were developing traits that would define true mammals. In the shadows of giant archosaurs and emerging dinosaurs, cynodonts quietly refined the blueprint for the mammals of the future. The seas, too, flourished with reptilian giants. Ichthyosaurs reached lengths of 30 feet, streamlined like modern whales, diving deep into the oceans. Plesiosaurs grew larger and more specialized, with with long necks or massive skulls designed for different hunting strategies. Ammonites and other shelled invertebrates rebounded in dazzling diversity, filling the seas with spiraled shells of every size and shape. The Triassic world was rich, dynamic, and alien, a place where crocodile-like Rauisuchians ruled the land, ichthyosaurs patrolled the seas, and the first dinosaurs remained minor players. Yet in this crucible of competition, change was coming. A series of environmental upheavals and extinctions would soon strike again, shattering the dominance of the Rauisuchians and leaving an opening for the small, agile dinosaurs to rise. By the late Triassic, life on Earth had recovered from the Great Dying and surged into new heights of diversity. Rauisuchians stalked the plains as apex predators. Prosauropods grew into the first true giants, and the seas teemed with ichthyosaurs and ammonites. Dinosaurs were present, but still minor players. Swift, lightly built, and overshadowed by their more imposing reptilian cousins. But Earth's story is never static. Just as in earlier ages, forces beyond the control of life itself were about to change everything. Around 201 million years ago, at the close of the Triassic, another wave of cataclysm struck. This event, known as the End Triassic Extinction, would topple the reigning giants and hand the world to the dinosaurs. The trigger came from deep within the Earth. As Pangaea began to break apart, colossal rifts tore open the crust, unleashing some of the largest volcanic eruptions in history. Vast lava flows spread across what would become the Atlantic Ocean basin, and with them came floods of carbon dioxide and sulfur gases. The climate lurched into chaos, extreme warming followed by pulses of cooling, acid rain scouring the land, and oceans turning anoxic once more. The Rauisuchians, once apex predators, could not withstand the turmoil. Their dominance crumbled, and they vanished into extinction. Many large amphibians, remnants of earlier ages, also disappeared. In the oceans, marine reptiles suffered heavy losses, and ammonite populations crashed before rebounding again in new forms. It was a global reset, though not as devastating as the Great Dying. For dinosaurs, however, it was opportunity. Small, fast, and adaptable, they endured where their larger rivals failed. Free from the shadow of the Rauisuchians, they began to expand into roles that had once been closed to them. Herbivorous sauropodomorphs grew larger, evolving into the long-necked giants that would dominate the Jurassic. Theropods diversified into new predators, from fleet-footed hunters to apex carnivores. Even early ornithischians, the plant-eating lineage that would later produce stegosaurs, ceratopsians, and hadrosaurs, began to establish themselves. By the dawn of the Jurassic, the balance of power had shifted. Dinosaurs were no longer rare experiments on the fringes of ecosystems. They were becoming the central figures of a new age. What began with small creatures like Eoraptor and Herrerasaurus had blossomed into a dynasty that would rule the planet for the next 150 million years. The Triassic had been a crucible, a time of survival, experimentation, and repeated upheaval. From the ashes of the Great Dying, it had forged the ancestors of mammals, the masters of the seas, and the first dinosaurs. Now, with the extinction of their rivals, the stage was set. The Mesozoic, the age of dinosaurs, was about to begin. In the closing chapters of the Triassic, the dinosaurs began their true ascent. They had started small, light, and fast, living in the shadows of Rauisuchians and other dominant reptiles. But after the End Triassic extinction, those shadows lifted. The great predators of old were gone, and the stage lay open for the dinosaurs to claim. The earliest sauropodomorphs, like Plateosaurus, had already hinted at the grandeur to come. With long necks and sturdy legs, they grazed on conifers and cycads, gathering in herds that reshaped the landscapes. Their descendants would become the colossal sauropods of the Jurassic. But here, in the Triassic, they were still learning to stretch toward the sky. Theropods, too, began to grow bolder. Chelophysis, a slender predator about 10 feet long, hunted in packs, its narrow jaws lined with sharp teeth for seizing prey. Swift, agile, and intelligent, it embodied the traits that would make theropods the most enduring carnivores of the Mesozoic. From these beginnings would come the great tyrannosaurs and raptors of later ages. Even the earliest ornithischians, small, bipedal herbivores with leaf-shaped teeth, began to carve their place. Though modest compared to their sauropodomorph cousins, they represented the first stirrings of lineages that would one day produce armored stegosaurs, horned ceratopsians, and herds of duck-billed hadrosaurs. The rise of dinosaurs was not sudden, but steady. With each generation, they grew more diverse, more adaptable, more central to the ecosystems of Pangaea. By the dawn of the Jurassic, they had spread across continents, inhabiting forests, floodplains, and deserts alike. Their reign had begun, not yet the thunderous dominance of later ages, but a confident stride to the role of Earth's new rulers. The Triassic had started as a world of survivors, scarred by extinction, shaped by archosaurs of every form. It ended with dinosaurs stepping forward, ready to define an era. From here, the Mesozoic stretched ahead, 150 million years of dominance, evolution, and wonder. But to understand that reign fully, we must always remember what came before. The experiments, the failures, the forgotten empires of creatures that lived and died in ages long past. The story of the dinosaurs is inseparable from the story of the worlds that prepared the way. When people think of prehistory, their minds almost always leap to dinosaurs, the thunderous giants of the Jurassic and Cretaceous, the icons of lost worlds. Yet as we have seen, the story of life before dinosaurs is just as grand, just as strange, and perhaps even more important. For nearly 4 billion years before a dinosaur ever walked the Earth, our planet was alive with other rulers. Trilobites scuttling across Cambrian seas, armored fish prowling the Devonian rivers, dragonflies with wings like eagles drifting above carboniferous swamps, and saber-toothed gorgonopsids hunting in Permian deserts. Each of these dynasties rose, flourished, and fell, shaping the stage for what would come next. Without them, dinosaurs could never have emerged. The ecosystems of the Cambrian explosion taught life to experiment, building complexity. The reefs of the Ordovician and Devonian gave structure to oceans. The forests of the Carboniferous transformed the atmosphere, filling it with oxygen and laying down the coal that humans would one day burn. The synapsid empires of the Permian tested warm-bloodedness, differentiated teeth, and upright postures, traits that would pave the way for mammals. Even extinction events, devastating as they were, served as turning points, clearing the slate and opening opportunities for survivors. To look at Earth before dinosaurs is to realize that life is not defined by one age or one dynasty. It is a story of constant renewal, of trial and error across deep time. The forgotten kingdoms of the past are not mere preludes to the dinosaurs. They are chapters in their own right, each with lessons etched into the stone of the earth. The history of life before dinosaurs is also a history of survival against overwhelming odds. Again and again, our planet was rocked by catastrophes, global ice ages, volcanic eruptions, sudden climate shifts, and the deadliest extinction of all, the Great Dying at the end of the Permian. Each time, life was brought to the brink. Each time, most of what existed was swept away. And yet, survival never stopped. In the Ordovician, when 85% of marine species vanished, tiny jawless fish endured, carrying forward the vertebrate legacy. In the Devonian, when placoderms and reefs collapsed, lobe-finned fish clung on, evolving into the first tetrapods. In the Carboniferous, when giant insects thrived and forests fell, reptiles with amniotic eggs secured the path to land. And in the Permian, when synapsids ruled and nearly died with the Great Dying, a few small lineages, synodonts and dicynodonts, survived, ensuring mammals would one day inherit the earth. Survival was rarely about size or strength. More often, it was about adaptability, the ability to endure changing climates, shifting food sources, or hostile conditions. It was the small, the overlooked, the resilient that carried the flame of life across the ages. This lesson, written again and again in the fossil record, speaks to us today. Dominance may be temporary, but adaptability ensures survival. By the time the first dinosaurs appeared in the Triassic, Earth had already lived through half a dozen forgotten worlds. Dinosaurs did not arise in a vacuum. They inherited a planet sculpted by all that came before. From the fishes of the Devonian, they inherited jaws, limbs, and the blueprint for vertebrate success. From the forests of the Carboniferous, they inherited oxygen-rich skies and landscapes shaped by plants. From the synapsids of the Permian, they inherited ecosystems with apex predators, grazers, and armored herbivores. Roles dinosaurs would one day step into. Even the mass extinctions that paved the way for dinosaurs were part of their inheritance, erasing competitors and leaving open niches that only they were poised to fill. Dinosaurs rose not because they were destined to, but because of timing, opportunity, and adaptability. When the Rauisuchians fell at the end of the Triassic, dinosaurs were ready, small, agile, and resilient. From those humble beginnings, they expanded into every form imaginable: towering sauropods, horned ceratopsians, armored stegosaurs, swift raptors, and titanic carnivores like Tyrannosaurus rex. Their reign lasted over 150 million years, longer than any mammalian dynasty to date. And yet, even the dinosaurs were not forever. They too faced extinction at the close of the Cretaceous. Their story, like the synapsids and trilobites before them, was part of the same cycle: rise, flourish, fall, and leave the world to others. What mattered was not their end, but what they passed on. Birds, the last living dinosaurs, carry their legacy in our skies today. The story of life before dinosaurs is not just about creatures long gone. It is about us. Every step of that journey shaped the world we live in. The coal of the Carboniferous powers our cities. The oxygen of ancient forests fills our lungs. The evolutionary experiments of synapsids gave rise to mammals and eventually to humans. We are not separate from this story. We are its latest chapter: the trilobites, the armored fishes, the giant dragonflies, the gorgonopsids. All of them are our ancestors in spirit, part of the lineage of life that flows unbroken across 4 billion years. When we dig into the rocks and uncover their fossils, we are not just looking at dead creatures. We are looking at pieces of ourselves, fragments of the journey that led here. And the lessons of these forgotten worlds matter more than ever. They remind us that no dynasty is eternal, that dominance can be fleeting, and that adaptability is the true currency of survival. They remind us that Earth can change suddenly, dramatically, and without mercy. And they remind us that even after the darkest extinctions, life finds a way to recover, reinvent, and thrive again. So when we think of dinosaurs, as magnificent as they were, we must also think of what came before. The trilobite seas, the armored fish rivers, the dragonfly skies, the saber-toothed deserts. These were the ages that built the foundation, the forgotten empires that prepared the way. Before the dinosaurs, there were worlds just as rich, just as strange, and just as vital. Their legacy is written not only in stone, but in the living world around us, and in us. The dinosaurs may be gone, but the story of life, written long before they came, still continues, and we are part of it.